Good evening, gentlemen. Welcome back to the old computer shack. In the previous video, we talked about building a super spiffy, ultra deluxe KVM switch that can take many different types of video input formats, including VGA, 15 kilohertz analog RGB, digital RGB, and composite video. Switch them all into one VGA monitor. Part of that problem is converting CGA or EGA or MDA graphics into VGA. Now, CGA and EGA and MGA are TTL-level RGB signals. They have an R, a G, a red, green, and a blue component, as well as some sync signals. CGA also has an intensity signal. And these signals are all either on or off, either 0 volts or 5 volts. So between the 3 color bits and the intensity, you get 4 bits for a total of 16 colors out of VGA. Now, in contrast, analog RGB, the red, green, and blue channels have a maximum peak-to-peak voltage of around 7/10 of a volt. Some monitors let you go up to 1 volt, but I think 7/10 of a volt is the official standard. And their sync signals are also still TTL levels, 0 and 5 volt square waves on VGA for the synchronization signals. But VGA also operates at generally at a minimum of 31.5 kilohertz. So we have two separate problems here. One, we have to convert the CGA voltage levels to something that is compatible with analog RGB, aka VGA. And then, since CGA is only going to be running at 15 kilohertz, we have to double that to 30 kilohertz so that it will display on all VGA monitors. There are some VGA monitors will sync down to 15 kilohertz, but not very many. So for the latter problem of scan doubling is what we call doubling that the sync rate to 30 kilohertz from 15. We can just use this the ubiquitous GBS 8200 board. This was designed for adapting old arcade cabinets to newer monitors. Now, if you look at this board closely, it claims to support CGA and EGA. Well, that's not the kind of CGA and EGA that you're thinking of. Apparently there are two entirely different definitions of CGA and EGA. There is the IBM definition, the TTL CGA and EGA standards used by computers, and then there's also an analog RGB standard, CGA and EGA, that operate lower than 31.5 kilohertz. So all this does is resample analog RGB signals. So we can use this, they're cheap, we can use this to get the scan rate up to something compatible with a VGA monitor and get that VGA output. But we still have to worry about voltage level conversion before we feed that CGA signal into this board. And since the analog RGB standard has just red, green, and blue inputs, it doesn't have an intensity input. We also have to try to figure out some way to include that intensity bit out of CGA, make it change the voltage of these analog RGB signals so that we can get all 16 colors. Because if we ignore the intensity bit, we'll only get 8 colors. And that's no good. So, if you have never watched a man who has alcohol-induced brain poisoning, alcohol-induced brain damage, try to do math. Well, you are in for a mighty good time this evening. Hey guys, it's Lee from the future all of a sudden. Let me cover this up because you haven't actually seen this yet. There you go. So hey, I just wanted to mention before I do this stuff that several of you, Black Upion in particular, have sent stuff in the posted stuff in the comments section about your own implementations of this kind of circuit, and I just wanted to say before I do this myself that I really super duper appreciate all of your all's input in the comments. The whole reason for me doing any of this shit is to have interesting conversations with you guys about this stuff. I've found all of the stuff that you guys have sent to me and talked to me about very interesting, and I don't want you to feel like I'm snubbing your contributions by figuring out how to do this myself. It's just that figuring out how to do it is half the fun, right? So what's probably going to happen is I'll figure out how to do it, and then I'll decide that my design's a piece of shit, because it probably will be, because I don't know what I'm doing, and just make yours anyway. But in the meantime, back to the past now, before I had quite as much White Claw. Okay, here we go. So, let's begin by drawing a picture of the CGA signals that we will need to deal with. Hopefully I can remember what I'm doing here. So, the signals that we need to mess with from CGA are the red signal, the green signal, the blue signal, the intensity signal, the horizontal sync signal, and the vertical sync signal. 6 signals. There's a 7th pin on the CGA connector that is a ground. I think the Commodore 128 uses one of the normally unused pins as a composite video output on the 80 column port 2, but maybe it might be pin 7, I don't know, I haven't read the manual for a long time. So we need to convert all of these signals into something compatible with this analog RGB board, which accepts a analog red signal, a analog green signal, a analog blue signal, and a composite sync signal. Alright, now at frequencies higher than 31.5 kilohertz, this board does accept separate horizontal and vertical sync signals, like CGA gives us. But because of the way the firmware on this board is written, if we're trying to scan convert signals lower than 31.5 kilohertz, as is the case with CGA, we have to give it a composite sync signal. So in addition to converting these 4 voltage levels into these 3 much lower voltage levels, we also have to somehow combine these horizontal and vertical sync signals into some kind of TTL-level composite sync signal. We'll do that later too. Anyway, each of these signals are digital, either on or off, 5 volts or 0 volts, 5 volts or 0 volts, 5 volts or 0 volts, 5 volts or 0 volts. All 6 of these signals are like that. Alright, the analog RGB signals range from 0.0 to 0.7 volts. Alright, so let's first ignore the intensity signal and figure out how we're going to convert this. Let's just start with the red signal. We can replicate it, the same circuitry for the green and blue signals. How are we going to convert this red signal here from 0 or 5 volts into 0 or 0.7 volts? Well, let's draw a little schematic here. Imagine we have our red signal coming out of the computator, and it goes through a resistor, that we will call R1. This is our digital RGB signal, and it goes on out to a VGA connector, an analog red signal. And in addition to this one resistor here, we'll also take another one. We'll put it right here and tie it to ground. We'll call this R2. What we have here is the classic voltage divider. Now I'm sure that to many of you, this is like super basic, boring ass shit. So if that's the case, just, don't watch it. I won't be the least bit offended. But I'm not an electrical engineer, nor am I even a particularly skilled amateur. So this kind of basic shit is still kind of interesting to me. So I hope it's interesting to you too, but I imagine it's not, so sorry about that. Alright, let's see here. So, this is our classic voltage divider right here. Two resistors tied to ground, a voltage input here and a voltage output taken between the two resistors. Recall, let's see here. I'll just derive the equation for that because I can't remember what it is off the top of my head. Recall that, according to Ohm's law, voltage equals amperage times resistance, right? Now, we're going to call this V in, and we're going to call this V out right here, okay? Now, the total resistance here, well, let's rearrange this equation first. We're going to say that I is equal to R resistance over voltage. Amperage is equal to resistance over voltage. So, the V in, if we measure V in from here to ground, alright, V in is going to be R1 plus R2 over V in, right? I is going to equal R1 plus R2 over V in. Alright. Likewise, if we measure the voltage between V out and ground, right here, we can say that I here is going to equal R2 over V out. Am I doing this right? It's been like many decades. Okay, so we can set these equal to each other now, these two equations. We can say that R1 plus R2 over V in is equal to, see, R2 over V out. And then we can turn these all upside down because that makes things a little easier to deal with. V in over R1 plus R2 is going to equal V out over R2, and then we can rewrite that as V out equals V in times R2 over R1 plus R2. And that is the equation for calculating the output voltage of a classic voltage divider circuit like that. Don't ask me to prove Ohm's law, I don't remember how to do that. So, if we're going to be going from 5 volts here at our V input down to 0.7 volts down here on our V output, alright, we can start filling in numbers in this equation down here, right? So we've still got two variables here to deal with, these two resistor values. The easiest thing to do, in my opinion, is to just kind of almost arbitrarily choose a value for R2. Now, we don't want to choose too low a value for R2, or too much current will flow through this circuit and she'll get too hot. We don't want that. We don't want to draw too much current. We might fuck stuff up, draw more current than the stuff on this side can source and stuff like that too. So we don't want to do that. Likewise, we don't want to choose too large a value for R2 because that'll negatively affect the switching speed at the output of the circuit. So to make the math easy, I'm going to arbitrarily set R2 equal to 1K. Alright, so now we've got all of our values but one here, and we can solve for R1 right here to convert this TTL level RGB input from 5 volts down to 0.7 of a volt. So to do that, we'll say that V out's going to be 0.7 volts, and I'll go ahead and divide 5 volts out of that right there, and R2 is equal to 1K, and that's going to be over R1 plus 1K. Alright, so now we got to solve for this shit. We can just cross multiply that. Why am I so drunk? 5K equals 0.7 R1 plus 0.7K, and then we can subtract. That'll be going to be 4.3 K equals 0.7 R1. Divide all this by 0.7, and we get, I can't do that fucking shit in my head because I'm too dumb. Hang on a second. I'll get my calculator out of here. 4.3 divided by 0.7 is going to equal, so R1 is going to equal about 6.14 K. That seems right based on previous circuits that I've made. So that's going to be, so if we look at our where is it here? Okay, derp. Yeah, if we look at our equation here, we can see that as R1 gets larger, the output voltage will get smaller, right? So we don't want to exceed 0.7 of a volt. So of course we're not going to find a 6.14K resistor anywhere, but we can pretty easily find a 6.2K resistor. So we'll say that R1 is going to equal 6.2K, and that'll give us our 0.7 volts on the output. We have 3 bits, red, green, and blue, so we can get 8 colors out of this. But we're forgetting about the intensity bit. We somehow, when the intensity bit is low, we have to lower this output voltage. Let's just say 0.35 volts. I think it's actually supposed to be a little higher than that, so in the final circuit I'll probably use some variable resistors so I can tweak stuff. But for the purposes of figure eight, we're gonna say that when the intensity bit is high, we want to output a whole 0.7 volts over here. All right. When the intensity bit is low, when it's 0 volts instead of 5 volts, we want to output about half of this over here. So how are we going to do that? Well, if we take our intensity bit and run it into this circuit 2, we're going to put a diode right here, pointing in that direction. We're going to go up here, and we're going to tie into this circuit here, and we're going to add another resistor right here. And I'm going to call this, I'm going to change this to R2A, and I'm going to call this one R2B. Alright? So, when the intensity bit is high, this diode will keep current, it'll go to 5 volts. This diode will keep any current from flowing into the circuit in this direction. Alright? So that basically just makes this resistor float. Alright? So we can pretend that this whole part of the circuit is gone when the intensity bit is high, and we'll get our 0.7 volt output like we calculated before. Now when the intensity bit goes low, this will start to act like a ground, right here, and the diode will let current flow in this direction. So this resistor here will add its pull down power, if we want to call that, alongside this one and drop this voltage right here. So we have to somehow figure out the value of R2B such that we can get an output voltage of about 0.35 volts here. So, how are we going to do that? Well, while I is low, this diode will always pass current in this direction. Alright, and we can think of this as a ground right here. So we can kind of redraw this circuit. I mean, like, conceptually, we can look at this circuit more like this. We've got our V input of 5 volts, and it comes through this R1 resistor. Alright, and then it comes out to our V out, which is going to be 0.35 volts in this case, and we've got 2 resistors in parallel going to ground like this. Conceptually, we can think of this circuit like this. You can't see that very well on camera, can you? We can think of this circuit like this whenever I is low. So this is going to be R2A, R2B, and this is going to be 6.2K, this is going to be 1K, and we need to solve for R2B. So how are we going to do that, boys? Well, recall that when you wire resistors in series, figuring out the total value is very easy. The resistances are just additive. You just add them all together when you wire resistors in series. But when you wire resistors in parallel like this, the relationship between them gets a little more funky to calculate. So the formula for finding the total value, so if we want to treat all of this as just one resistor in the circuit, right, we can find the total resistance from this point to this point, right, using an equation like this. 1 over the total resistance will equal 1 over the value of R1 plus 1 over the value of R2 up to plus 1 over the value of Rn, where N is the last resistor in your parallel resistor network here, right? So this is of course very tedious to solve for an arbitrary number of resistors, at least on paper. But if we just assume that we're only going to ever have 2 resistors in parallel, we can forget about this part of the equation right here, and we can just say that 1 over total resistance is equal to 1 over R1 plus 1 over R2, and we can simplify that. We can solve this for RT. We get something like RT is going to equal what? R1 times R2 over R1 plus R2, right? Yes. So, yes. Right. Yes. Okay. So once we've got this total resistance value here, we can replace these with R2A, R2B, R2A, and R2B, and we can call this R2. So, alright, so I had a little bit of a mathematical fuck up there. Like I said, alcohol-induced brain damage. So, let's try this again. We had determined that RT was going to equal R1 times R2 over R1 plus R2 for solving these parallel resistor networks like this. So we can go back to our equation that we had derived before for finding the output voltage of a voltage divider like this, except everywhere we see R2 we can substitute in this conglomeration of shit right here, right? So our output voltage we want to be about 0.35 of a volt is going to equal 5 volts. I'll go ahead and divide that out on that side. Is going to equal And R2A we know is 1K, right? So we can go ahead and replace that with a 1. So what we end up with is R2, which is going to be R2B over R2B plus 1K. Alright, and that's going to be over the value of R1, which is 6.2K. Alright, plus R2, which once again, considering that R2A is 1, simplifies to this shit. Over R2B plus 1, right? Are we having fun yet? So yeah, obviously from here we can solve for the value of R2B. You probably don't want to watch me do that because I'm sure that this bullshit is boring enough already. It's going to equal 875 ohms. Alright, 875 ohms. We've got it figured out there now, right? That should work on each of our RGB channels. Now we can't be tempted to just use one diode here on the intensity bit, but if we do that and then say we have like a G channel down here and we tie them together like this, you know, and have another one coming to ground here, you know, like that, right? This is upside down and backwards, but just for illustration's sake. So say we just used one diode here, and say like red was low and red was high and green was low, it would draw current all the way through here, and that would make our intensities get fucked up depending on what other bits we're on. So we've got to put a separate diode in each of these RGB channels here when we convert between our 0.7 and our 0.35 volts. And like I said, I'll probably use variable resistors right here for both of these, so that I can kind of tweak this a little bit and get the intensities just right. And for horizontal and vertical sync, turning that into composite sync, there are two different ways to do that. Now in VGA, that's still a TTL signal. It's 0 and 5 volt square wave, right? I think the proper way to do this, maybe I've got this backwards. I think the right way to generate composite sync is to use an OR gate on both of these. But there's something wrong with the firmware on these GBS 8200 boards where it requires a non-standard C-sync. So I think you actually have to generate composite sync with an XOR gate on these things, which is fairly easy. I mean, other than having to use an extra fucking gate on here for no reason. You just put your exclusive OR gate in here like that, and that turns into C-sync. And that feeds into the C-sync pin on this thing here, I believe. Or there's a pin on this header here too. And then everything's happy. And we should get 31.5 kilohertz VGA out of this thing after inputting this, what'll end up being a 15 kilohertz analog RGB signal that'll come out of this conversion circuit. So clear as mud, I guess. We'll try to build this next time. I'm still waiting on particularly I don't have any high density DB15 connectors, so we could go ahead and build this, but I wouldn't be able to hook it up to a monitor. I wouldn't even be able to hook it up to this thing really. I want to use that VGA port. Well, wait a second, that VGA port doesn't have composite sync connector on it. I'll have to use that little port right there. Anyway, yeah, so TLDR is I don't have all the parts I want to have yet, but next time, if you actually come back next time after being bored as shit after watching all this fucking scribbling, I will have a better schematic drawn out and we will test this theory that we have come up with this evening, and we will find that there are two colors in the CGA palette that this won't work for. There's a brown color that requires a little bit lower red signal, and there is a, basically when RGB are all 0 and intensity is 5 volts, that's supposed to generate a dark gray color. But the way we've got these diodes in here right now, it's just going to generate black for that, I think. So we'll have to come up with a way to fix both of those signals. And I think I've got some ideas on how to do this. It'll probably turn into kind of a clusterfuck. And then I've got an even better idea about how to do all of this. But I want to try this on some breadboard first, as soon as the rest of my parts get here. But I see a lot of implementations of this kind of thing that don't use a voltage divider. They just use a resistor. All right, and in order for that to work, the VGA monitor would have to draw a constant current or something. Maybe do the RGB signals on a VGA monitor all have internal 75 ohm termination or something? Could we just hook up a resistor and then assume that R2 is going to be inside the monitor and is always going to equal 75 ohms, and calculate these two resistor values from that? Or is this the right way to do it? I don't know. I don't, like I said, I'm not even a skilled amateur at any of this shit, so I don't quite understand how, other than trial and error, people have come up with the correct resistor values to do this with just a straight resistor rather than using a voltage divider here. Maybe I'm really missing something, but I mean, in order to know that, you'd have to know the current draw of the monitor, and you would think that that would change depending on the monitor, wouldn't it? I don't know. Anyway, thanks for joining me. I'm sure you've probably gnawed your own arms off if you're still watching past this point, but I appreciate you joining me anyway. And next time, I promise, no, I don't promise. Next time, hopefully, we'll do something that isn't quite as boring for you to watch, but I hope that if this wasn't already just like stupid basic stuff for you, like it ought to be for me, even though it isn't because I'm dumb, I hope that you found it interesting and informative and educational nonetheless. Alright, see you guys next time. Do you like my festive Halloween pencil? I used it especially for this. Yeah, alright, bye.